In computer networks, we are looking at chapter number 1, Introduction. Packet switching and circuit switching. So, the networks, there are two types of network basically, or the communication they follow. How the data flow, the routing it takes place. So it can be packet switched network, it can be circuit switched networks. And these packet and circuit, they have come from some background. Packet switch is connectionless, circuit switch is connection oriented. So in packet switching, every packet is routed independently of every other packet. So we have two messages here. They are taking different routes. Okay, for example, we have multiple routes, multiple path, multiple way, because in between this A, B, C, D, E can be routers, it can be switch, it can be the different network devices, connections. So this message, let us assume that we have a packet. This message is a packet. Now this packet size is say 4,000. Now we divided it into say 3,000 or divided into 3 parts. Now there are 3 parts. Now the first part can take this path. It can be routed through, the other one can be routed through this path. And the other one can again take a different path. So every packet is routed. Route means the path it takes, independent of every other packet. I'm not saying that all these 3 will not take, they can also take a single path also. Now what is the benefit? If this C router goes down, I showed you 2 and 3 are going, they have to go through C, or they were going through C. But now when the system, some part goes down or the router goes down, the packet switching system will dynamically reconfigure itself so that the next packet, that is if 2 and 3 were supposed to go through C and C is down, then the packets can take different routes. That is, they can take this way or they can take this way, the other subsequent packets. Ultimately, they have to reach destination. There is one more thing here, that if too many packets, they swamp, they flood the router, it can choke the router. So what will happen? The packet will be lost. The router will be, or the networking devices will be losing or dropping the packets. This is losing of packet, and this happens in packet switching. You can call it as swamping, flooding, choking. This all results in losing of packet. This happens in packet switching. Circuit switching, it doesn't happen, right? We'll take the differences also, short way of discussing these two. So the sender will notice and resend, but the quality of service can be poor because you don't know, or there has to be some way, it has to be accounted which packet was dropped, which wasn't. So the quality of service of packet switching is not as compared to the circuit switch networks. For example, you are sending an image. Now you are sending it using packets, a message. Now the eye or knows this packet is lost. How do you see yourself at the destination? Now the other counterpart is circuit switching. It has come from telephone systems. Normally in telephone system, there are 2 parties. One is the caller, callee. So 2 parties, one calling, one attending. Now when you pick up the cradle, you dial the number, and then the other person will listen to some ring. And when he picks up the call, both of them picks up the call. now a permanent connection is established, right? A permanent connection is established, and this is the single route I'm talking about. And this route or connection will be maintained until the call is terminated by either of these two. Now, what happens when the line or the switch or the some networking devices goes down? The call will be aborted. So there is a circuit. How does this circuit form? One is calling, one is replying. So there is a kind of circuit being formed. That is why this is called circuit switching. The call has to be aborted if something goes down in between. Therefore, circuit switching is less fault tolerant than the packet switching. Okay, packet switching is all about taking different paths. Even if there is some fault, it can tolerate it. The packets can take another part, another route, right? But here, there is no other path, a single path. So circuit switching, because what is the benefit? First of all, there is a single path always established. So the quality of service, it can support easily. Because when the connection is being established, in advance. So the communication network or the subnet can reserve the bandwidth, link bandwidth. It can also, switch the buffer spaces. Also the CPU time. This all comes under the quality of service. And for example, the resources are not sufficient. If you know that there is a call already being established, then what will happen? Previously, when we used to call, 10 years back, after 11 o'clock, the calls were free. So everyone starts calling. And when we start calling, it is always busy. But once the connection is set up, the connection of circuit switching will give you a good service. So here, once you make a connection in circuit switching, the packets or the path or the route will always be the same for all the packets. There are equipments which we see today in the core network. Both are packet also and circuit switched equipment also. Mostly the core networks, they are still using the packet and the circuit switched equipment both. These are not different networks. The network or the communication medium, they have the same merging of this packet and circuit switched network. The older mobile phone networks, they used to have this circuit switched core network because they were carrying the voice calls. I'm talking about the 1G systems. But that legacy, that tradition is still seen in the latest 4G, 5G network UMTS. You see MSC, Mobile Switching Center, all I have tried to show here. So MSC, Mobile Switching Center, then we have GMSC, that is Gateway Mobile Switching Center. Then we will also see the Media Gateway, MGW. These are there for switch service. These are actually the circuit switched core network, like previously in PSTN, public switched telephone network, like the BSNLs we have. So still we have the combination of these two. Okay. So circuit switch is still there, packet is also there. What are the differences between a circuit switching network and the packet switching network? How the connection will be established? Circuit switching is the connection oriented. Packet switching is connection less. Packet switching is unreliable. Circuit switching is reliable. How? See, In circuit switching, when you call, there is a permanent route established. That is, the physical path between source and destination is established. So this is the physical path when you are using a circuit switching network. While you are using a packet switching network, there will be no permanent path for the packets. One packet, the other packet, they may take different route. They can take different path. The ultimate thing is they have to reach at the destination. No matter, they take the path independently. In circuit switch, if something breaks, the connection breaks. But here, in the packet switching, if some portion goes down, then also the packets will reach, they will take a different route. In circuit switching, because the permanent path is established, so we can reserve the entire bandwidth in advance, right? Because the circuit switching, we know in advance. But the packet switching, this bandwidth is not reserved. So the packets use the same path in circuit switching. The packets travel independently, and when it comes to the bandwidth, which comes under the purview of quality of service, we can reserve the entire bandwidth in advance. As I said, packet switching we cannot reserve because different links can be established, different route can be taken for independent packets, right? Now, the other difference between circuit switching and packet switching is the bandwidth wastage. And packet switching, there is no bandwidth wastage. Bandwidth, you can think of a pipe. How much the width of the pipe is, that decides the bandwidth. So bandwidth is wasted in circuit switching, not in packet switching. In circuit switching, there is no store and forward transmission. Packet switching, it supports store and forward transmission. Now in circuit switching, once you establish a path, there is no need to store. The packets have to take the same path every time. But in packet switching, first it has to go here. Now it has to look for the path. It has to decide the route. There are routing algorithms. So if some of the link is broken, the packets may take different path. So it has to come and then it has to go. So it has the packet switching support the store and forward transmission. There are various generations of mobile telecommunication, or you can say mobile networks, or mobile services, cellular services, data services. These are different generations: 1G, 2G, 3G, 4G, 5G. So the first generation was mobile phone system only transmitting the voice calls. There was only analog signals, no digital, no bits. Now you see here AMPS, Advanced Mobile Phone System. This was deployed in United States in 1982 and it was the widely used first generation system 1G. This G stands for generation. Second generation, now it switched to transmitting voice calls in digital form. Okay, now digital came here. This was to increase the capacity, to improve the security, and then the text messaging was offered, texting. Then GSM. This GSM is actually a 2G system, global system for mobile communication, and this was deployed in 1991. 1G 1982, 2G 1991. So this is I am showing how the phone used to look. 3G, this was initially deployed in 2001 and now it was giving both the voice and the data services digital. So it's digital voice and broadband digital services. So ITU International Telecommunication Union, they have specified 3G that if you are standing, you must get at least 2 Mbps, and if you are moving, walking, or in your train, you must get at least 384 kilobit per second. Mbps is megabit per second. This has to be the speed to call it as a 3G. And then UMTS. See, in between 2G and 3G, there is a time. So the CDMA 1 and GPRS, they all come in 2.5 G. We don't generally talk about 2.5G, but you need to know that there was 2.5G also. Some people have, they have researched on it. They have talked about it. So this UMTS is the main 3G system which was deployed worldwide. And as we take the example of YouTube, say, there is some upload and there is some download. So this kind of thing, you can think that there is a downlink speed 14 Mbps, uplink 6 Mbps. Now there is a spectrum, electromagnetic spectrum, and there is a radio spectrum. So radio spectrum. Now for the 3G system, the spectrum or the frequency range is very scarce, is very short. Now why it is related? Because you need to talk on certain frequency. You can only talk on certain frequency. Mainly in the mobile telecommunication, you ought to use the frequency. Okay. Now this frequency or band, this is governed by the federal government. Like that is, the government has all the right. They sell it that this is the range, and if you want to take this range, give us this money. So if you have a spectrum part, that is a licensed spectrum, now it becomes very easy to make systems and design systems according to it. Because at that particular spectrum, if you have purchased that spectrum, that is the frequency range, then you can make your own apparatus, design and operate the systems. But this costs a lot. This costs serious money. Let me take you to 2000. In United Kingdom, 5 3G licenses, they were auctioned by the government for $40 billion. I am talking about 2000. We are in 2022. So because of the scarcity of this spectrum, we have to do certain thing. So then came the cellular network. This cellular network has come just because of the scarcity of spectrum. There has to be done something to reuse the frequency. Okay. Because if somebody is talking and if other person is also talking, same frequency, there will be interference, and that interference, how to avoid that? So the coverage area of that base station was divided into certain cells. So if the division is such that there is a proper arrangement so that the two people talking may not interfere, or they may reuse the frequency. Okay. So within a cell, a user are assigned channels. For example, this A I am showing. All the A which you see here, they are in the same coverage area, but they do not interfere with each other and not also with the adjacent cells. These two, when they are talking, they don't interfere. So this is allowing this way of reusing or cellular network dividing into cell resulted in the frequency reuse in the neighboring cells. And this is how the capacity of the network with a same frequency was increased. So this is the latest arrangement which we use. Frequency reuse is a very important aspect in cellular network. Along with this, the usage of different kind of antennas like directional antenna, like sectored antennas on the cell towers. This also helped in reducing the interference further. So these are all the way how we use these different G systems and frequency reuse. 4G and 5G. These are the 4th generation and 5th generation system. Why we are just discussing them differently? Because now we are only talking about the data. That is, the voice is also now on data. That is the 4G, which was basically 4G LTE, which actually became popular, the long-term evolution. This LTE 4G offers faster speed, and this came up in the late 2000s, and at that time various technologies were there. But when this 4G LTE networks they came, they, for the mobile internet especially, they outspaced the WiMAX, which was 802.16. WiMAX was a very popular technique, but it was overthrown by this 4G LTE. And 5G technologies, they are promising speed of 10 Gbps. And they 2020s, many countries got it, and it's still under said deployment. 4G, it uses frequency bands up to 20 megahertz. But 5G, they are designed to operate in much higher frequency ranges or bands, up to 6 gigahertz. See, 20 megahertz, we are talking about 6 gigahertz. That is this 6 gigahertz, that is a high frequency. Now, what are the challenges? High frequency means a lot of attenuation, a lot of interference. Because of this, newer algorithms are being made, the technology are being emancipated. That is, say, MIMO, multiple input, multiple output antenna arrays have come up. And the thing is that these short microwaves of this range of frequencies, they are easily absorbed by rain. So this is also one of the challenge which the designers are experiencing and working on. Wireless networks or Wi-Fi. Sometimes people also call it as wireless fidelity. But here the 802.11 is the IEEE. Wi-Fi is the formal name. Now Wi-Fi is using those spectrum which are unlicensed. Most of the frequencies which we see are licensed by the government, which the mobile cellular the network also use. But here the Wi-Fi is using the unlicensed band, and this has been given to ISM this for industries, S for scientific, M for medical usage, for research purposes, for these three different, because government cannot sell this to these also ISM. So ITU-R has bands 902 to 928, that is for industry, and 2.4 to 2.5 gigahertz is for scientific usage. And these are free band, unlicensed band. We can use it if you are working in any of these fields. 5.725 to 5.825 gigahertz, this is for medical. So these are reserved unlicensed band. Wi-Fi is using this. So 802.11, they have clients. This can be your mobile phone, this can be your laptop, and the infrastructure, that is, we have access points, or we already know it by the name of base station. And since Wi-Fi has a range, so it is installed in a building, an area, a range, and these access points, see, the laptop and the mobile phones are wirelessly connected to access points. But these access points are connected through wire. They are wired connected. So there is a backbone of wired network. And these clients, they are talking to access points. So the systems have to go through access point, then only they can talk. But there are certain ad hoc networks like MANET, etc. If they are in same radio range, they can talk directly without an access point. This is also possible. Now, when we are dealing with the wireless networks, the frequency which we use in 802.11, these are radio signals. Now sometimes they can be reflected off the solid objects, which is the objects which we find generally as infrastructure, the buildings, etc. And because of this, the multiple echoes of transmission, they may reach a receiver along different path. So this different path, for example, one may reinforce, two signals may reinforce, or the two signal, they are coming out of phase, so they may cancel each other. So this kind of phenomena of cancelling is called as multipath fading, and this is very natural, and most of the design issues are along this with this discussion only. So if you see here, if some reinforcement is there, you will get a non-faded signal and even higher. But if it is cancelling, the two signals are cancelling each other, you will get a faded signal. So what is the solution? Path diversity is the solution. So this has come to overcome the variable wireless condition. So we can take different multiple independent paths to send the information, not sending in one direction, but different paths. That is why it is called path diversity. And the information shall be received even if one of the path is giving you a faded signal. So the initial 1997 I'm talking about standard, this defined a wireless LAN that was running at 1 megabit per second and 2 megabit per second. And this was using frequency hopping. That is, it hops. It changes the frequency. One frequency it is working, then another frequency, then third frequency. So this was frequency hopping going on. And using the SPED spectrum, that is whole of the spectrum which is being assigned, whole of the spectrum is being used. Okay, spreading the signal across the allowed spectrum. This was 1997. Now the technology emancipated. So the spread spectrum design, it was even more extended, and it became the 802.11b standard in 1999, and the data rate increased 11 Mbps, then 802.11a, then 802.11g. These standards, there was a new modulation scheme they adopted, and we'll be talking about this OFDM, which is actually orthogonal frequency division multiplexing. And this OFDM is what? To just give you a hint, this is all about slicing. That is, it divides a wide band of spectrum into very short, very narrow slices. Over these slices, different bits are sent in parallel. So this is how the frequency selective fading is less. So this becomes less sensitive to the frequency selective fading. This is the picture I wanted to highlight. We'll be talking about this in detail. And there are different versions giving different speeds. So we have AG, AC, AD, and this AD I'm talking about because it will work only in the indoors because it cannot penetrate the wall. Okay, so we will have the extension and the extender kind of thing. But here you see IEEE standards are there, 802.11a and 5411b 11 Mbps. These are the data rates. G 54 Mbps and 600 Mbps, AC 1.3 Gbps, and then we have AX 10 to 12 Gbps. And you mark the frequency range 2.4 gigahertz until 5 gigahertz. Now, since the wireless is a broadcast medium, it goes to everyone. So 802.11 has to deal with a collision problem. Because collision means two packets can collide. So in order to handle this, 802.11 also uses CSMA, carrier sense multiple access. And this CSMA, you see here, this is the classic wired Ethernet. It was used in classic wired Ethernet, 802.3. And then came the Aloha. So this CSMA and Aloha, actually the collision detection and avoidance scheme is taken from them. So here, very simple algorithm, computer or the computing device wait for a short random interval before transmitting. And if someone is transmitting at that time, it will again wait for the next transmission. And this scheme really worked well in the wireless environment, Wi-Fi environment. It was not working that well in the wired networks. I'll give you a scenario here. How does it work? See, suppose this computer A is transmitting to computer B. But the range of A and C is not there. That is, the radio range of A transmitter is too short to reach computer C. Now, if C wants to transmit to B, it can listen that if someone else is transmitting. But as you see in the picture, A and C cannot talk. They don't know about each other. But if C starts transmitting, and you know already A has started transmitting, there will be collision. So once this collision happens, what will happen? C has started sending, A was already sending. Because A and C are not in range, there will be collision. What is the solution? Here, the sender will wait for a random time and it will retransmit the packet. In Wi-Fi, there is another challenge which is called as mobility. Once you hand off, that is, if the mobile client or mobile phone or a laptop, it is moving from the access point, it has to hand it off to the next AP, that is access point. For example, you have a house. If you go to certain place where there is no signal, what will you do? Then you can use the extender or you can say the booster. So the solution is that it can consist, the network 802.11 can have multiple cells with multiple APs. There is one more issue, that is the security in the broadcast wireless transmission. Because, we have we don't want it to be received by anyone else. So 802.11 standard has included, is there encryption. If you are sending AB, make it as XY. When it reaches to the sender, it can be decrypted to AB. AB is sent, making it as XY. That is the basic idea of encryption. So WEP was very popular, wired equivalence privacy. But finally this was broken because it was the encryption technique. And then came in the 802.11i, it was replaced by Wi-Fi protected access. Initially it was called as WPA, Wi-Fi protected access. But now it has changed to WPA2. These are the encryption techniques. There is one more, authentication also there. So in 802.1x, here we have the certificate-based authentication for the access point. Client has to take the authentication, then only it will be able to access the Wi-Fi or wireless network. So mobility and security are also the issues in wireless transmission. Network protocols. Now this we are going to take in the next discussion. Till then, thank you so much. Take care of yourself.